Why Mandelbrot? Chapter 5, The Dimensions. Chapter 1 was the secret sauce. Chapter 2 was about complex variables. Chapter 3 gave you the algorithm to create your own Mandelbrot creation. Chapter 4 was about Mandelbrot's monsters. And you can find all of the chapters, including this one, Chapter 5, The Dimensions, on my website, fractallog.com. fractallog.com. Let's talk about scaling just for a little bit here. When you take a square of 2 dimensions, you scale it, you have a scaling factor of 1/2. You basically turn it into 4 pieces of fragments or masses of the original. Taking 1/2 actually turns it into 4. And the formula that works throughout all of these, what they call self-similar graphics, is that you take the scaling, which is 1/2, and you raise it to the dimension of the thing you're dealing with, which in this case is 2 dimension, and you get how many fragments you get when you're all done down here. So, and this works across the board. Here's the cube over here. If you scale it by 1/2, you've got 3 dimensions, so you cube it, and that means you should have 8 pieces when you're all said and done. You got 1, 2, 3, 4, 5, 6, 7, 8 pieces. So this formula works. And what happens is you can take this formula and transpose it, and it's the same exact thing as saying the scaling factor raised to the d power is equal to the fragments when you're said and done, or the mass we'll call, is equal to 4, which is the mass. So, and what happens is you can do a log on that, and it comes out to be that the d, which is the dimension, is equal to log base 2 of 4, log base scaling factor of the fragment or the mass. And so if you know any of those, you can find, if you know 2 of them, you can find out the 3rd one. And there is a rule that says if you want to get rid of the log 2, you can put it this way. You can put log 4 over log 2, and it's the same exact thing. And of course, any log table will tell you that that's 2, and that corresponds with our original dimension. So all this works together. If you didn't know this, all you knew was this, you could compute d, and the same over here, because 2d is equal to 8 is the same, 2 raised to the d power is equal to 8 is the same as this. And you do a log on that when you have d is equal to log 2 of 8, and of course we can get rid of the log 2 by making it as a denominator. And you go to any log table and it'll tell you that's 3. Well, that corresponds with the dimensionality of that particular object. So we're gonna be talking a little bit in the next few slides about scaling and the scaling factors and mass fragments of the original after we do our scaling. And we're going to be looking at the use of this formula. So here is what they call a self-similar object, which means once you scale it down, you have basically the same thing as you had when you started, only smaller pieces of it. So it's self-similar. And the same kind of rationale over here. We take the scaling factor is 1/2 in this case, and as well as the fragment or the mass count is 1/2. So we have a 1/2 raised to the d is equal to 1/2, which is the same as saying this. And of course, that's the same as having d is equal to 1. Well, we already knew that. D is equal to 1. So all that adds up. Now notice over here that Hausdorff in 1919 came up with this for self-similar graphics. He basically said if you want to find the dimensionality of the object, you put the log of the mass or the fragments of the original over the log of the scaling factor, and it will tell you the dimensionality. Very handy, very nice. That's the Hausdorff equation. We've already looked at the squares. We've got the same thing going on we looked at before. The scaling factor is 1/2, the fragments 1/4. 1/2 to the d is equal to 1/4, and so on and so forth. You turn log 2(4) into log 4/2, which is 2. We already knew that, but this confirms that this is how you find the dimension of a self-similar graphic. You can use the Hausdorff. Here's the same thing as we did with the cubes, dimension 3, same thing exactly. We'll find out log 8 over log 2 is 3. We already knew that. Third dimension. It's all working out. Now we can use it on something we don't know. Let's look at the Sierpinski triangle. Very interesting shape here. And if we take 1/2 of it, basically it's taking one of these guys here, one of the triangles, because that's 1/2 right here, 1/2. And so that's the scaling factor. But what happens down here is, look at this. How many of these do you need to build the other one back up? Well, you need 3 of them. So there the fragment or the mass is 1/3, which means you need 3 of them to go back to the original. And so over here you have the scaling factor is 1/2, the mass is 1/3, and this equates to this particular equation, which gives us log 3 over log 2, which is 1.584, so on and so forth. What that says is the Sierpinski triangle, the dimension of the Sierpinski triangle is 1.58,49625. Right there. Very interesting. Van Koch, snowflake. What about it? We take 1/3 scaling factor because we've got basically we've got 1 unit here. We take 1/3 of that, and we have a little self-similar object that it takes 4 to build it back up. It takes 1 here, 1 here, 1 here, 1 here. But we're going to take one of those self-similar objects by taking 1/3 scaling factor, and we bring it down. And we come to find out that, as we said before, it takes 4 to build it back up. So the fragment of the original is 1/4. So over here we have 1/3 raised to the d is 1/4. And we come up with log 4 over log 3, which is 1.2618595. That is the dimensionality of the Van Koch snowflake in accordance with the Hausdorff formula. These are all self-similar classical graphic objects.
A man named Hausdorff in 1919 introduced a number which was just a mathematical joke, and I found that this number was a good measurement of roughness. When I first told it to my friends in mathematics, they said, "Oh, don't be silly, it's just something." Well, actually, I was not silly.
Mandelbrot needed a formula for roughness because he was dealing with monsters. He wasn't dealing with the classic graphic figures. And when he chose Hausdorff's equation, everybody laughed. They thought that was funny. And he said, no, it's no joke. That's the formula that I'm going to use. Because he was dealing with things like coastlines and fractal shapes. An example, not a line, not a square, not a cube, or Sierpinski triangle, not a Van Koch snowflake, not even necessarily self-similar, although it could be. Fractal roughness. He needed something to gauge fractal roughness. Perhaps he needed a new methodology. How about counting boxes? So we can establish a square grid around the object, and we can assign the size of a unit. I'll call it scaling factor 1. And then we can count the boxes. So we got 14 boxes that are touched with scaling factor 1. We have scaling factor 1/2 gives us 29 boxes. 71 boxes for scaling factor 1/4, and 174 boxes touched with scaling factor 1/8. So now we have a summary for scaling factor 1, 2, 4, and 8. We have boxes touched 14, 29, 71, and 174. We're going to take the log of those. You'll find out why that is in a minute. So the log of 1 is 0, so on and so forth. And the log of 14 is 2.64, so on and so forth. The random island falls into a fractal category, unlike the previous classic shapes of being self-similar. So we need an additional level of uncertainty here, something that will allow us to plot a line on this graph so we can find the best fit line and come up with the best answer or the best estimate that we possibly can for that random coastline. So instead of doing it this way with a Hausdorff conclusion, we'll do it with, we added a C, which is a constant, and it allows us to plot something on the line on the graph, and it allows us to give us the best fit using that constant, and we can do what they call linear regression to find the best fit. So if we established the constant here in this formula, very similar to this, and if we worked it out to its conclusion, we would have something very similar to the Hausdorff, but we'd have a minus log C that he doesn't have. But what's interesting here is right before we get to this level, we come up with this formula, which is very interesting because it resembles the formula for a line. If we were to plot log n and log s and use log c as the intercept and d as the slope, we could actually make a line out of this data. So what we'd do is we would put log n on the y-axis, and we'd put log s on the x-axis, and log c would become the y-intercept, and d would become the slope that we're looking for. This is the dimensionality of that random coastline. That's what we would be looking for. So to plot out this line, we're going to be using a free application that can be downloaded from GeoGebra. Handy little tool that you first have to establish a spreadsheet, and you lay out your parameters, and it'll help you draw the line that you need. So here's the video of making that line. I'm going to get a spreadsheet, and we're going to fill in the spreadsheet with the scaling number, the number of boxes touched, the log of the scaling number, and the log of the number of boxes touched. So here we have 1, 2, 4, and 8. And here we have 14, 29, and 71, and 174. And here we have equal to log this one, and we want to extend that down there. And here we want to have log of this one, and we want to be able to extend that down here. Actually, that was incorrect. Let me try that again. We don't need that one right there. Okay, So, and then what we want to do is we want to graph this line, okay? So we go over and we want to get a list of points, and we're going to call that list 1. I'm going to create it. So there's our list of points. And then we want to come down here at the bottom. We want to do a fit line. And for the fit line, we do a list 1. Like that. And so there we have the best fit line for those particular points. Now all we got to do is find the slope of that line. And we come over here and we make an equation out of it with a y. So here we have the equation is y is equal to 1.22x plus 2.59. And what that means is that the slope of that line is 1.22, and therefore the dimensionality of that random island is also 1.22. So let's check out the results of our linear regression. We wound up with a line equation y is equal to 2.59 plus 1.22x, where 2.59 is the y-intercept and 1.22 is the slope. So looking over here, these are the 4 points that we are graphing right here, with only one exception, and that is we told GeoGebra that we wanted 2.64 to intersect with x0, and the line actually didn't give us that. It gave us 2.59 down a little bit lower, and the reason for that is that it tried to fit the best line over those 4 points. So the only point that was a little off was the last point down here. So it really is not a big deal because it doesn't really change that much of the line. But I just wanted to point out that there was an adjustment in the best fit function. But you can see these other one, the 2.08 and 5.16. 2.08 and 5.16 and so on and so forth. You can see them intersect all the way down this line of slope 1.22. Now, there's one other thing to say about this, and that is that if you had a larger sample set, if we had a scaling factors in the order of 20 and 25, then perhaps the slope of the line might not be as steep. It might be a little bit smaller, as it was in this case here. Instead of being 1.22, it turned out to be 1.19, which is slightly less steep and slightly less rough. So the rule of thumb is that the more scaling factor samples that you get, the more accurate the linear regression will be. So when we dealt with self-similar objects, we went through this particular protocol using the Hausdorff equation from 1919. But when we entered the fractal objects of Mandelbrot, we added a constant which put some variability in the equation, and we had to turn to a linear regression of a line on a plot, on an XY plot, to get the best approximation. And so here we have Mandelbrot's contribution to fractals, fractal roughness. Fractal roughness. Let's change the subject momentarily to the complex plane. Complex plane consists of real numbers and imaginary numbers, and any point on the plane will have a certain real component and an imaginary component. Mandelbrot did most of his work within this circle of radius 2. Anything outside the circle of radius 2 was of no interest to Mandelbrot. In fact, he specifically, his quest was to discover all of the black pixels within this circle, and that is what he called set C. The question here is, why did he get a picture of a baby when he discovered set C? Why does it have that shape? And is that all there is? We don't think so. We think there's more to it than what Mandelbrot discovered. If we let X represent the real numbers, and if we let Y represent imaginary numbers, then what we have here is an object on the XY plane representing the complex plane. And this particular figure, as you can see, is a Mandelbrot baby. The mathematics that was used to create this baby is the original recursive formula as specified by Benoit Mandelbrot. What we are going to be doing here is we're going to be realizing that what Mandelbrot has done is all of his work has been done on this two-dimensional plane right here. Everything he did was on this two-dimensional plane. He neither had the computer power, nor the capacity to be able to look on either side of that plane. But we do today, and we can think out of the box today. And what we're going to be doing is we're going to be able to see what happens to that Mandelbrot baby as it leaves its comfortable two-dimensional world and enters into a world where Z becomes positive and Z becomes negative. Before we talk about 3 dimensions, let's talk about how Mandelbrot handles 2-dimensional. Here's an example of 2 points. One point is not a member of the Mandelbrot set, and one is a member. And here is how it's handled in the recursive equation. The recursive equation is fed the red point right there. It's fed throughout the equation, and it results in this component. This component is fed into the recursive equation and results in this one, so on and so forth, until finally, after 1, 2, 3, 4, 5 iterations, there's a border violation. What that means is that the next point it's calculating has just jumped out of the circle of radius 2, and therefore it is not a member of the Mandelbrot set, nor is it a fractal. It's rejected. So that is how we handle where the points are. And this one says that this point doesn't belong. Feeding the yellow point into the recursive formula, here it is, feed it in there, results in this component, feed it in, so on and so forth. You keep doing it. And down after 4 iterations on this particular point, we have a well-behaved, stable set of numbers here. And in fact, if these numbers were continue on beyond 4 iterations, if they were gone to 1,000 iterations, they would never jump out of the circle of radius 2. Therefore, they are set members of the Mandelbrot set. Let's talk about the 3D complex plane. Why don't people do a lot of 3D complex planes out there? Well, I know why. Because when I tried it, I had a lot of trouble. I could not add another axis just per se, just any old axis, because if I did that, I would leave the complex plane. And Mandelbrot's had to stay in the complex plane. The minute you leave it, you leave behind any resemblance of Mandelbrot. So I had to remain within the complex plane, and that presents a lot of problems. So to keep it in the complex plane, I had to name it I prime. Well, when you name it I prime, you're starting to do all kind of multiplications with i's and I primes. There's no rules for I prime. I had to set my own arithmetic rules up and teach my computer program how to handle that. Well, we already know that I times I is -1, and we already know that, and one of the things I had to set up was that I prime times I prime is -1, which makes a lot of sense. Then I had to do some association things like I prime times I is -1 and I times I prime negative. There's nothing exciting about any of these new rules, but on a computer program on its own, it would not know how to handle these. You have to teach it. And once I taught the computer program these new rules, there's only one change that had to be made. The recursive formula remained absolutely the same. The only thing that changed was the definition of C. It was expanded from AX plus BI to AX plus BI plus DI prime. That is the only difference. And here's what you get. You have to multiply 2 points that are 3-dimensional together, and that does cause some issues. But what I've done here, and you don't have to know this, I'm just putting it down for documentation purposes, that if you wanted to try it yourself, this is how to do it. Net result is you have to come up with these 6 entities in order to be able to multiply these 2 together to create another point in the recursive formula. Once you've created these 6 entities by doing the following, then all you have to do is to paste them into this formula here, which gives you the new 3D point. The real part of that point takes square 1 plus square 2 plus square 3 plus cross 3 plus A2. A2 is the original real component of C. And then you come up with the imaginary component by adding cross 1 with B2. B2 is the imaginary component of the original C that was fed to the program, was fed to the recursive equation. And then to find out the new I prime value, the extended imaginary part, you have to add cross 2 with D2, and of course D2 is the original extended imaginary component of C that was fed to the recursive formula. If I know this sounds very complicated, and I know it sounds busy, but once somebody does that, as I have, here are the kinds of things that you get. This is a Mandelbrot baby. This Mandelbrot baby is sitting on an XY plane, X and Y, obviously representing real numbers and imaginary numbers. And if we view him from the top, we can see that he is sitting on Z is equal to 0. So a two-dimensional XY plane sitting at the very center of the Z axis. As far as the x-axis is concerned, it's a normal Mandelbrot. It goes from -2 on the x all the way to a positive 0.5 on the x. And on the y, it goes from a little over 1 to down a little over -1 down here. Normal Mandelbrot baby. This is a sibling of the Mandelbrot baby. You can see it's placed about 1 unit in front of the baby on the positive z-axis, 1 unit. You can also see that it's approximately 1 unit down in distance from the top, from the Mandelbrot baby, which means that it's exactly 45-degree angle from its sibling, the Mandelbrot baby. Notice it's also malformed. There, I made the background a little bit less black so you can see the deformation of this offset sibling of the Mandelbrot baby. It's deformed. It's moved 45 degrees down, 1 unit down, 1 unit away, which equates to a 45-degree angle. We have just added another sibling. This time it is 1 unit back and 1 unit up, 45 degrees toward the negative on the other side of the Mandelbrot. And it too is degraded in shape. If you'll notice, there's an inverse there. This shape degradation occurs in this part of the baby, and this is on the outside, so they're exactly inverse. There's symmetry from the outside in, but the two babies, the two siblings, are the opposite. Notice that this one has many more fractals on the top than this one does, so it's exactly inverted. But they are the Mandelbrot's siblings. We've just added another sibling. It too is 1 unit positive and 1 unit down, which is 45 degrees down from this unit. And notice it's very much more degraded than its brother. So as you can see, we've added another sibling, 1 unit back, 1 unit up, 45 degrees from its brother. We look at them from another angle. You see they're all 1 unit apart from one another. We can see that there's symmetry between the two. We can see the 45-degree angle developing. Now, it needs to be pointed out here that we could do this an infinite amount of times. We could have a solid row of babies all the way through here, and it would be a solid row of red fractals, until it got to the end. Notice what happens at the end. turns into black. And the truth of the matter is that these black pixels go on forever. Okay, they go on forever. Let's pull it back to the original view that we looked at. Turns out that this one goes off into positive infinity as a black line eventually, or it turns into 2 or 3 lines, about 10,000 units down, but it keeps going to infinity. And this one turns into the same thing, 2 to 3 lines, about 10,000 units up, and goes on to infinity, to positive infinity. This goes to negative infinity, obviously. So what we are talking about here is the MandelFash fractal log. That's what these represent. Together, if we were to fill all these in, we would have a log that goes on forever, comes out of negative infinity, goes all the way to positive infinity. We've added one last shape. We have added what is called the horizontal Mandelbrot. It is an exact copy of the original Mandelbrot. The exact copy. It's what you get when you slice the log this way or slice it this way at exactly the center. You get 2 Mandelbrots, one going one way and one going the other way. So we'll put this back into the position it was when we first found it so we can get oriented here. So what we have then is we have all of these siblings, plus we have this horizontal right there, which, as you can see, kind of joins the 2 deformed babies together with the original Mandelbrot. Just at the very end, where the feathers on top, the very top of the tip fin, they meet together and connect. Very interesting. Very interesting. This is the MandelFash fractal log. When you put all the babies together, you have a fractal log. Here's a little video of 1/2 of the MandelFash fractal log. This concludes Chapter 5, The Dimensions. We have now covered the secret sauce, complex variables, the algorithm, the monsters, the dimensions, and the last chapter is entitled Universal Patterns. And these are patterns throughout the universe, throughout nature, that speak to fractals and relate to what we're doing with regard to Mandelbrot. Stay with us. Thank you.